Concavity is having an outline or surface that curves inward like the interior of a circle or sphere. A point of inflection is a point on a curve at which the curve changes from being concave down to concave up or vice versa.
A derivative is a function which gives the slope of a curve or the slope of the line tangent to a function. Velocity is the same thing as the first derivative. The second derivative is the derivative of the first derivative, which is also known as acceleration. So today we're going to be teaching you about the relationship between f of x, f prime of x, and f double prime. So to start, I'm going to draw a graph. This is going to be f of x. F of x.
So now we're going to plot the derivative of this graph. So notice where we have relative extrema in 3 separate points. So at these separate points, the derivative is going to be at 0. The derivative will be positive because the position function is increasing. So you can do a little line right there. From the extrema on down to the relative minimum, you can see that the position function is decreasing. So the derivative is going to stay 0 or below 0 until this point. And from here, the position function starts to increase, so the derivative will be positive until the next relative extrema, where it begins to start decreasing. And that is your derivative.
And so the first derivative has relative extrema here and here. So the second derivative will be 0 there, and then right there. And so from this point to that 0 is decreasing, so it will be negative. And then it begins to increase until this point where it begins to decrease once again. There is the second derivative. So now that we've drawn both the first derivative and the second derivative, we can see the relationship between the second derivative and the position function. The second derivative has zeros at both this point and this point, which means that the position function has inflection points here and here. An inflection point is where the position function changes concavity. So we can clearly see that the position function is concave down from here to here because the second derivative is negative, and it's concave up from here to here because the second derivative is positive, and then concave down again from here to here because the second derivative is negative.
There's a really easy trick to remembering the relationships between the position function, the first derivative, and the second derivative. It can be displayed through a smiley face. So here, we have the second derivative. So next we have the nose, or the first derivative. And then we have the position function, or the mouth. So this is the second derivative. So where the position function is concave up, like a smiley face, the first derivative is going to be increasing, and therefore the second derivative is going to be positive.
The relationship between the functions can also be shown as a frowning face. So we have the second derivative will be minus signs for the eyes, a nose pointing downwards, and then a frowning mouth to show that it is concave down. And so when the position function is concave down, the first derivative will be decreasing and the second derivative will be negative.
So here we have the velocity graph. So starting with our first question, where can we find where s of t, or the position function, is increasing? Now, if you recall from what we've said earlier, the position function is increasing where the derivative is going to be positive. So from 0 to 2, the position function is increasing because this graph is positive from 0 to 2. Our next question, where is the position function decreasing? The position function is going to be decreasing from 2 to 4 because the velocity graph is negative from 2 to 4. And our third and final question, where the position function has relative extrema. So, the position function is going to have relative extrema where the velocity equals 0 or does not exist and goes from negative to positive or vice versa. So we're going to have one place where there's relative extrema at x equals 2.
Our next questions would be about where the acceleration, or a of t, is negative. And the acceleration is going to be negative when the derivative, or v of t, which is our graph here, is decreasing. And v of t is decreasing from 1 to 3, so acceleration would be negative from 1 to 3. Our next question would be where a of t, or acceleration, is positive, which would be where our velocity is increasing. Acceleration is positive from 0 to 1 because the velocity is increasing. It is also positive again from 3 to 4 because the velocity is increasing once again. Our last question is about where acceleration would be 0. Acceleration would be 0 at points on the velocity function where it has relative maximum or minimums. And so in this function, it would be at point 1, 2, and point 3, negative 2. So at these areas, the acceleration would be at 0. This is the graph of acceleration, also known as the second derivative. We have the first 3 questions are about the first derivative, and we're going to use this graph to answer them. Our first question is find where v of t, or the first derivative, is increasing. The first derivative is increasing when acceleration is positive. So acceleration is positive from 0 to 0.5, as well as from 3.5 to 4. Our second question is about where velocity is decreasing. Velocity is decreasing when the acceleration is negative. The acceleration graph is negative from 0.5 to 3.5, so velocity will be decreasing at that point. Our final question is about relative extrema of velocity. Relative extrema happens at points on the acceleration where it is 0 or does not exist and changes signs. This occurs at 0.5 and 3.5.
Our second set of questions are about the position function. So our first question is where the position function is concave up. So a position function, if you remember the smiley face, is going to be concave up where the acceleration, or the second derivative, is positive. So it's going to be from points 0 to 0.5, and then again from 3.5 to 4. Our next question is where the position function is concave down. So this is going to be where the second derivative is negative. Second derivative is negative from 0.5 to 3.5. Our third and final question is about where the position function has points of inflection. The position function is going to have a point of inflection where the second derivative equals 0 or does not exist and changes signs. So that would be at points 0.5 and 3.5 because the second derivative equals 0 and goes from positive to negative or from negative to positive. So now we're going to draw the derivative when given the position function. So you see here that we have relative extrema. So the easiest points to start with are the relative extrema because we know that the derivative is going to be 0 at these points. So we can draw in the points for the zeros. And then from there, it's fairly simple. So from here to here, the position function is increasing, so the derivative is going to be positive. And then from here all the way down to here, the position function is decreasing, so the derivative is going to be negative. Then again, from here to here, it's increasing, so it's going to be positive. from here to here, the position function is decreasing, so the derivative is going to be negative. And then from here to here, it's positive, or increasing, so the derivative is going to be positive. And that is our derivative. So now we have learned how to accurately be able to identify the relationship between the position function, first derivative, and second derivative, and we're able to use this information to then draw the derivative of a function. Given the graph of the original function, we have 2 send-away problems that you can do on your own to help you further your learning on this topic.